Afternoon. So today we're going to look at the chain rule, and we're going to have the chain rule is really used when we're being asked to derive composite functions. Now the chain rule is written as dy dx equals dy du times du dx. And I'm just going to write this out twice just to explain the implications of this. So if we consider this function from the standpoint of algebra, okay, dd du cancels out and it leaves equals dy dx. Now we can use this principle when we're dealing with any form of composite function. So an example, or a simple example, might be to consider, okay, and I'll just write it in different notation. Okay, so if we were asked to find the derivative of fx and fx equaling x plus 3 all squared, what we may do, and I might just write it in terms of y initially, is you might look to write it as x plus 3 all squared. You might expand the bracket, and then you can find the derivative simply by just deriving that expanded expression. However, when we talk about doing it using the chain rule, and the chain rule is quite effective because sometimes it's not so easy to expand a bracket. What you would do here is you say let u equal the embedded function. Now the embedded function is the function within the other function. Okay, it's the function that is within the composite function. So we're going to say let u equal x plus 3. Therefore, du dx equals 1. We say, therefore, y equals u squared, and dy du equals 2u. And therefore, dy dx equals du dx, which is going to be this, 1 times 2. And we're going to substitute what our value of u was. So x plus 3. And we get 2x plus 6 if we expand it. And we can see here that both this value and this value are identical, and therefore they're correct. Okay. Now that's a simple example. But if you were asked to solve a problem that was a little bit more tedious, so find dy dx of y equals x squared plus 3 to the power of 5. I'll just write it out a little bit neater. To the power of 5. So what we would say first of all is we would say let u equals, and we're going to use the embedded function, x squared plus 3 du dx is then going to equal 2x. That 3 just disappears. Therefore, y equals u to the 5. We're going to find dy du. That's going to equal 5u to the power of 4. And therefore, dy dx is going to equal 2x. That's taken from du dx times 5x squared. Might just get rid of that. 5 x squared plus 3 to the power of 4. And that will give us 10x x squared plus 3 to the power of 4. Now, one thing you might want to appreciate with these functions, especially with composite function, we can rewrite that in many different forms, and you may have expressions that are useful, that may not look the same, but they actually equate to the same. So just be wary that when you're finding dy dx, your answers may not be represented by what you might find in the back of the book as far as their answers, but it doesn't mean that you're wrong. You just need to make sure that you're simplifying as much as possible to go forward. Okay, so what I want to do is I want to have a look at a composite function involving a square root. And what I might do is I might even complicate it further. So this will be somewhat of a complicated question. So find dy dx of y equals 1 square root x squared minus 2x. Okay. The real work with this function is rewriting it so that you can work with it. So one thing that I would do if I was rewriting it is I would write this in the form of the bracket, and I would have to recognise that that's negative, the power is going to be negative a half. I've got 1 over a square root sign, that's the power to the negative a half. And then I would proceed with my chain rule. So let u equals x squared minus 2x. du dx is going to equal 2x minus 2. Y equals u to the negative a half. dy du, bring the power out the front, reduce the power by 1, so that's going to give us negative 3 on 2. And here what I might do is I might actually try to resolve dy du in terms of this whole expression of u. So I'm going to write it as negative 1, 2, okay, square root x squared minus 2x to the power of 3. Okay. And then what I would look to do is to state what dy dx is going to equal. Well, obviously it's going to be du dx, 2x minus 2, times negative 1, 2 square root x squared minus 2x all cubed. We can do a little bit of cancellation here. Okay, so let me just move this up a little bit further. So I'm going to recognise that that's going to be negative 2x plus 2 all on 2 square root x squared minus 2x to the power of 3. I'm going to cancel out the 2's here. That'll be 1. And what I might do is I might try to write the expression so that it looks a little bit more elegant. And I'm pretty happy with that as a simplified form, and I would say that that's correct. Now, one thing that I would note, or tips, simplifying, when you're simplifying, okay, use fractions where you can, or if you have to, don't avoid them. Okay, positive powers. So in this expression, I had the opportunity to just use negative 3 on 2, but I don't want to do that. I want to use a positive power like I have here with this whole expression being raised to the power of 3, okay? And avoid fractional powers. So it really depends on how well you can work with your indices and your surds in combination with one another. And that's just really when we're simplifying. So just make those notes.